Jagannath, and this is my Physics 2212 Lab 3 report. So the purpose of this lab is to experimentally and computationally compute the magnitude of the magnetic field produced by a bar magnet, as well as the relationship between the distance and the magnetic field. So as you can see here are the fundamental equations that you have to use for this process. The assumption that I made was that a bar magnet acts like a magnetic dipole, and then here were the results that I came up with. So the experimental setup, this is to find the location of the magnetometer sensor, which is the observation location. And as you can see detailed here in this slide, this is the process for how I did that. So to calculate the magnetic field on the axis, you have to basically take different distance measuring points, varying distances from the magnetometer sensor, and then graph the linear or the natural log of the magnetic field versus the natural log of the distance. And then that's this equation right here. So when you do that, the slope is the distance dependency, which as you can see is negative, because as distance increases, the magnetic field decreases. And then the magnetic dipole moment mu equals 2.15 amperes times meter squared. I calculated that by setting these two equations equal to one another and solving for mu, which is basically this right here. So for the off-axis magnetic field, you use the same process as the on-axis, except you have to calculate this perpendicular distance here. And then when you do that, the magnetic field in a y direction is equal to the measured value minus the Earth's magnetic field, because the Earth's magnetic field is also a component here that's coming into play. So when you end up with a magnetic field of 6.44 times 10 to the negative 5 teslas. So the observation questions here, when you're far away, there's a near zero magnetic field, and as you get closer, it just increases. So the computational model, this is the equation for the magnetic field due to a magnetic dipole, and when you code that in here with the same value here for the magnetic dipole moment, what I ended up with was a value of 2.7 times 10 to the negative 5 for the teslas for the computational value of the off-axis B field. And so this is the difference here between the two. It's a slight difference since the experimental conditions weren't perfect. They are still in the same order of magnitude though. So some sources of error are other magnetic fields, such as other electronic devices and light towers, and then slight movements of the phone when moving to complete the measurements for the on-axis field. So the what-if questions: what if you hadn't oriented your experiment to compensate for the magnetic north? This would have just made the results a lot more difficult and caused a lot more room for error, since the Earth's magnetic field would have directly interfered with the magnetic field created by the bar magnet. And then if you were to just stick two identical magnets together end to end, this would just increase the values of the magnetic field, since there are more magnets, so the direction should still be the same. So thank you very much.